Okay, well, this is basically the recent advances that we have made in the analysis of circular data using non-negative trigonometric sums. And basically, I will give an introduction, and then I will talk about the univariate case, and then I will the multivariate case. Let's see. Well, it's known by all of you that circular data basically is data that is recorded in the unit circle. You have orientations. Also, you can have the time of occurrence of different events that can be treated as circular data. Of course, that implies that common statistical methods cannot be applied, such as trying to take the mean of two angles. It doesn't make sense. And we have to work just with the angle of the mean resultant vector. We have some examples of circular data, famous data sets, particularly the Florence Nightingale Rose diagram, the time of death in the Crimean War. And we have also durations taken by animals, such as ants and turtles. And of course, wind directions is one of the most common data that you can have in terms of univariate circular data. Of course, the density function of univariate circular data should be non-negative, should integrate to 1, but also should be periodic. Common cases, the von Mises and the Grappet models. Many of these models, as has been discussed in a previous presentation, are symmetric and unimodal. Yes. Then we try to generate a family of models that can be asymmetric, and also it can be multimodal. This is the family of non-negative trigonometric sums, NNTS, that is defined in that way because basically you see it is the norm or the square modulus of the Hermitian product of two complex vectors that can be expressed as a double sum of different trigonometric functions that is going to allow us to have a different number of modes, with the interesting characteristic that the parameter space is going to be the surface of the unity hypersphere. That is going to give these models a lot of geometrical properties that can be exploited in the statistical analysis of circular data. We have created an efficient modified Newton-Raphson algorithm on manifolds to obtain the maximum likelihood estimates in this kind of models. And here the vector of parameters is represented by the letter C. And of course, I is a unit complex number that is the square root of -1. Interesting also is that this family of circular distributions is nested. It means if you have the parameter m equals to 10, pues all the cases with m less than 10 are included in the case m equals to 10. In particular, the case m equals to 0 is the circular uniform density, and the case m equals to 1 is the cardioid density. Okay? You have here some examples of different cases of the NNTS densities with the case m equals to 1, that is always unimodal and symmetric, and then the case m equals to 2, 3, and 4. And in the right side, you have many cases with m equals to 4, in which not necessarily you observe 4 modes in the density. In that case, m is related to the maximum number of modes that the circular density will present, and not exactly the number of modes. The first advance that we made in these 3 last years is about circular uniformity tests using as alternative hypothesis the family of circular NNTS distributions. And what is very interesting is that if you calculate the characteristic function of the NNTS model, you find that it is just different from 0 in the values from -m, in the discrete values from -m to m. And what is interesting is that taking the sum of two NNTS random variables, you are going to get independent random variables, you are going to get another NNTS random variable with the parameter m equals to the minimum of the parameter m's of the components of the sum of independent random variables. That is, the family is closed under summation. You have here some examples. For example, in the first plot, you have the sum of an NNTS density with m equals 1 and m equals 2, and the sum is equal to a density with m equals 1. And other examples. And of course, you have what is the equivalent of the central limit theorem for circular data that has to do with the convergence of the sum of independent identically distributed random variables to the uniform circular distribution. You have here this plot representing that scenario. Then a circular uniformity test is just testing for, in the case of alternative NNTS circular distribution, is just testing for the case m equals to 0 against the case m different from 0. This is a non-regular test because the case of the circular uniformity is in the frontier of the parameter space, and then all the characteristics, asymptotic characteristics of the likelihood ratio test and also the wall test are not satisfied, and you have to deal with this non-regularity in the construction of the test. No? For example, the wall test is interesting because basically the wall test is implying that how different is a distribution from the uniform distribution, because how far is the estimate of C0 squared from 1. And the likelihood ratio is very easy to calculate, but again, it is not a non-regular case, and the critical values were obtained by simulation and then were interpolated, similar to what is done in econometric tests, taking regressions of the critical value against the value of m and the reciprocal sample size, the square of the reciprocal sample size, and the interaction term of the m and the reciprocal sample size. You can see that the R square is very high, making us sure that the interpolation is doing a good result, and the new test can be applied to any sample size. We applied this to a very famous data set on the time of occurrence of earthquakes, and we found that we don't reject the null hypothesis of circular uniformity for world earthquakes during the last century and also for Mexican earthquakes, even that the plot looks like there is a clear areas of modes with concentration different from the uniform distribution. The second application is independence testing. Here, what we do is to take the copula that defines the joint density of two random variables. Of course, if the joining function g is equal to the uniform, then you have independence among the random variables. And then we define the angular probability integral transform as 2 pi the distribution function evaluated in the random variable. That is a uniform random variable. Of course, we know that in the circular case, the sum of two uniform random circular uniform random variables independent is again a uniform random variable, and that's the idea of the test, just to take the empirical angular probability integral transforms and calculate the sum of them and test if the sum of difference of these angular probability integral transforms are uniformly distributed. You have some example here of famous data sets in which clearly we reject the null hypothesis of independence when we apply the proposed test of independence using the non-negative trigonometric sums. The third application is that was discussed in a previous talk also, is reflective symmetry. What happened in the family of non-negative trigonometric sums is that when you apply the condition for reflective symmetry, you find that the parameter, the complex number that represent the parameter vector of the NNTS density has to be real numbers in order to have a symmetric distribution. Then it's very easy to apply a test just to test that the complex parameters are real. And you have here some examples of different NNTS models with that are symmetric and multimodal. That is very difficult to find some models that are symmetric and multimodal in the practice. No? Again, you can apply the likelihood ratio test. Here, there is no problems of regularity, and you can apply it directly. And for example, in the case of the famous data set on dragonfly orientations, that is a very discussed. When you apply the test in the best Bayesian information criterion model, you find that the p-value in the case of the asymptotic is 2.5%, and in the case of the bootstrap likelihood ratio p-value is 8.4%, not rejecting the null hypothesis. For all the other cases, you clearly reject the null hypothesis, and this exemplifies that it's very important to define the M in which is going to be tested the hypothesis of reflective symmetry. Here is the original data set of dragonfly orientations, and you see the plot, the histogram of the orientations and the best symmetric and the best non-symmetric model. And you can see the difference in considering symmetric and non-symmetric models. Then we extend the model to be able to make regression models, time series models. In this sense, what we do is to project the angles, observed angles, are projected to the unit hypersphere by taking the vector of trigonometric moments. That means the observation theta k is transformed into the vector of trigonometric moments until certain order m. Also, again, m has to be defined to be the best value m to make the correct use of the regression models. And then when the data is projected to the unit hypersphere, that is the parameters hypersphere, we try to find the best gray circle or small circle that represents the regression line in the case of the hypersphere. This is done by minimizing the sum of squares with respect to the gray circle or small circle. And what is interesting is that in this procedure of finding the best gray circle or small circle, you find a transformation of the original data of the angles that can be used as a linear variable that can be applied to any of the common linear models used in practice to obtain the parameter estimates as a generalized linear model with the common libraries for linear data. Here as an example is a famous data set on blue periwinkles angle and distance, the direction taken with distance. And you find here that when you make the transformation to linear data in the second plot, it's very clear that after some distance, about 25 centimeters, all the blue periwinkles are moving in some direction that clearly is the direction orthogonal where the C is located. That is the logical result that one is expected. Here are the conditional density functions that are obtained when applying the values of the estimated parameters on the small in this case, a small circle on the parameter hypersphere, and you can have all these probability density forecasts that can be used in practice. I will pass to the multivariate case. What we tried was to extend the non-negative trigonometric sum models to the multivariate circular case. Of course, now the data occurs in a torus, for example, in the bivariate case, in the surface of a torus. Of course, again, as in previous talks, well, the dihedral angles is one of the best known cases when this kind of models is applied. And what we tried was to extend the univariate model to the multivariate case. We take the same idea, just take the square modulus of the Hermitian product of the parameter vector with the vector of trigonometric models, but in this case, the vector of trigonometric models includes the different multiple trigonometric or joint trigonometric models of the different random variables. Again, in order to the density function to integrate to 1, we have a restriction of the norm of the parameter vector that has to be, again, in the surface of a hypersphere. Then we try to obtain all the properties of this model. Of course, it's a very difficult task because this is a quadratic Hermitian form that is not very easy to deal with in terms of the equations. But if we write the density function in terms of Kronecker products, we find that using properties of the Kronecker product, that basically what it says is that the product of two Kronecker products can be written as a product of a Kronecker product of the product of the original elements of each Kronecker product. And what we found were very interesting properties. The multivariate non-negative trigonometric sum is close on their marginalization. It means all the marginals of a multivariate non-negative trigonometric sum are non-negative trigonometric sums. Also, the conditionals are also non-negative trigonometric sums. Here are all the operations to demonstrate these results. And in some sense, is behaving like a multivariate normal distribution. It's close on their conditioning, is close on their marginalization, and the sum is close on their summation. It's very interesting that these properties can be proved very easily. Here you have just an application, just to finish, an application of wind direction, 7 different wind directions in the monitoring stations. And the best model corresponds to a parameter vector of n all with components equals to 3. And you can see the marginals obtained from the joint distribution that are having a good fit to the original data. And also you have some examples of bivariate densities obtained from the joint density, and also conditional bivariate densities. And here you have some reference, and that's it. Thank you very much for